Thanks. So I'm going to be presenting on how sensory history impacts both how we see the world and also our early visual processing. Serodependence is the influence of the recent past on perception and working memory. Working memory is typically studied in paradigms such as the continuous support task, where participants view a stimulus like an oriented gabor, and then after a delay, will rotate a dial to match that gabor as best as they can remember. These tasks are typically performed with hundreds or thousands of trials in individual blocks. And so each trial is performed in a context of the trials around it. So for instance, how you perceive the stimulus on this trial might be impacted by what you are holding in memory on the past trial. This exact effect was examined in a seminal study by Fisher and Whitney, where they sorted trials based on the relative orientation of the previous stimulus and found that participant responses were systematically attracted towards that item. So for instance, if at the current moment in time you're viewing this stimulus, and on the previous trial you viewed a stimulus 20 degrees clockwise, your perception would on average be attracted towards it by a few degrees. And that's what's shown by this distribution of errors, which is systematically shifted clockwise when the previous stimulus is 20 degrees clockwise. A central debate and people who have been studying this phenomenon since then is whether or not serodependence is an early sensory or phenomenon, or is actually implemented only in memory or by a later readout. And the fields kind of split. And so I wanted to kind of delve into this topic myself. Used a very simple paradigm to measure serodependence, and then I'm going to use bullet fMRI recordings to look at early visual activity and see how those representations are also affected by stimulus history. Briefly, participants viewed an oriented grading, and then after delay performed a 2 AFC task on a bar, which is clockwise or counterclockwise from that grading. An example trial looks something like this. We have a grading followed by a bar. We can look at the distribution of clockwise and counterclockwise responses and sort them by the change in stimulus orientation. And we found that, like the Fisher-Whitney study, responses were systematically attracted to the previous stimulus. We then wanted to look at representations in early visual areas. We used a retinotopic scan to select voxels for different visual regions of interest, and also used a separate localizer scan to identify voxels that were highly selected for orientation. We took the 100 most selective voxels in each ROI, and we used the activity patterns of those voxels to predict the orientation of the stimulus presented on a given trial. Here we're plotting our decoder's outputs on held out trials. On the x-axis is the presented orientation, and on the y-axis is the decoded orientation. And we see that there's a strong relationship between the two. Our decoder was able to do pretty well across the TRs of our delay period, as well as across different visual ROIs. We then asked whether these representations exhibited serodependence in line of perception or if they showed some other pattern. We took the output of this decoder and we looked at the decoding errors or residuals on each trial. We sorted those residuals as a function of the relative orientation change for the previous item to see if there was any bias. For this subject, we found that the residuals of the bias of our decoder was actually systematically repelled from the previous stimulus. And we found this pattern across ROIs and subjects. And this figure kind of summarizes our main effect, where perception shows systematic attraction, early visual representations show repulsion. We tried to make sense of this data using a model of gain adaptation. And our central main takeaway was that all plausible models that can explain our neural and behavioral data require readout to account for sensory adaptation. Thanks.